thank you very much. So yeah, this session is all about Vulkan on NVIDIA GPUs. Oh, my mouse stopped working. Okay. So who am I? My name is Piers Daniell. That's my Twitter handle. I'm a driver engineer at NVIDIA, and I've worked on OpenGL, OpenGL ES, and Vulkan. I've been a representative for NVIDIA at Khronos since 2010, and I've worked on OpenGL, OpenGL ES, and now Vulkan as well. My work at NVIDIA is I'm a technical lead for OpenGL driver updates, including OpenGL 4.1 through 4.5, and also OpenGL ES that we've added to the desktop driver. And with our newer tegras, it's the desktop driver that is used. And now I'm also a technical lead for the Vulkan driver at NVIDIA. So the agenda today, I'm going to break this down into two parts. A Vulkan primer. I mean, I'm sure there's some of you in the audience that probably have not yet learned much about Vulkan at all. So I'm going to go through what Vulkan is and why it's great. And then I'm going to talk a little bit about Vulkan running on our implementations and why it runs great on our implementations. So here's the Vulkan primer. So what is Vulkan? Vulkan was designed to meet all the demands that ISVs have been making over the last few years. Taking what they do with OpenGL and DirectX 11, for example, those older style APIs, Vulkan is a new generation API. And it's designed to reduce CPU overhead, which has been one of the big complaints. Scale well with multiple threads, which is something that OpenGL doesn't do that well. The other thing is it supports precompiled shaders, so you can do your shader compilation offline and send that into Vulkan. One of the key things about Vulkan is it is predictable, as in any kind of hitching or anything like that doesn't exist with Vulkan, because everything you do is explicit, and you do it up front. And when you do something, the work is done at that time and not later. There's no deferred validation like there is with OpenGL. It's also clean, modern, consistent API, and it starts with a clean base, so there's no historical craft or anything like that in it. And another really, really important thing about Vulkan is it supports mobile GPUs as first-class citizens, which wasn't quite so true with OpenGL. They had to do a lot of gymnastics in the background to make it run well on a mobile chip. But Vulkan, and I'll talk a little bit how that works. So why is Vulkan important? Vulkan is not the only next-generation 3D API. There's also DirectX 12, but DirectX 12 is Windows 10 only. There's also Metal from Apple, but Metal will only run on Apple platforms. So Vulkan is the solution for the rest of us. It can run anywhere, almost anywhere, anywhere from Windows XP all the way up through Windows 10. Or it can run on Linux and Linux-derived products like SteamOS. And it can even run on Android as determined by the supplier. And I'll show you a demo of running on one of our products. Oops, excuse me. So there's a lot of people behind Vulkan that are going to make it great. And these are some of the companies that are working in the committee, defining the spec and making sure it works well on their platform. And these are some of the software developers which are making sure that their API works and meets their needs. So you can see there's a lot of people that are working on this. So Vulkan is designed for all GPUs, from the low-power mobile all the way through to the high-performance desktop. It's all done through one API, so the application can basically write once, and if it's written well, that application will scale all the way from the low-power mobile processors all the way through the high-performance desktops. And it supports multiple levels of hardware. It can support GPUs that only support ES 3.1 level hardware, and all the way up to OpenGL 4.5 level hardware and beyond. And like I mentioned earlier, it supports tile-based hardware, just as well as it supports the regular feed-forward rasterizing hardware that we see on desktop. So when is Vulkan going to be released? Sometime this year is what Khronos has stated before. because it hasn't been released, I can't go into the nitty-gritty details of what exactly is in Vulkan, but I can talk about a lot of the concepts at a high level, which I will do. And of course, some of the things I mention may not be quite accurate when it's released, because things are still changing, but by this point, the API is getting pretty solid. One of the most important things that is our goal for Vulkan is that when Vulkan is released, we're going to release conformance, full conformance that covers all the features of the API. And the reason why conformance is so important is that one of the goals of Vulkan is to provide a consistent platform across all vendors, so that an API written on one platform can run just as well on every other platform. And the only way we can ensure this is to have a conformance suite that everybody has to pass, and a conformance suite which is thorough and has full coverage. And the only way an implementation can claim that they support Vulkan is if they pass the full conformance suite. So conformance is very important. It's something we're developing up front, and we already have a lot of contributions from many companies, and we will continue to add to it until it has full coverage. And the goal is that we want to release that when Vulkan 1.0 is released. So I'm going to describe Vulkan, the Vulkan API, and the high-level concepts by way of kind of touring through the steps that you need to do in order to simply draw a triangle, a hello triangle. So the steps I'm going to go through is talk about how the driver is launched from the application and how they create display for presentation, how to set up the resources, how to set up the 3D pipe and all the state, including the shaders, record the command for playback, and then submit the commands. Now, some of these concepts might not be familiar immediately at this point, but I will go through them, and hopefully by the end of this, you'll have a good understanding of the high-level concepts of Vulkan. So when an application starts, the first thing it talks to is the Vulkan Loader. Now, this is going to be an open source tool that is developed by Khronos in partnership with LunaG and Valve. The loader is a cross-platform component, so that the same experience running on Windows and Linux and other platforms would all be the same, going through the same loader interface. And the loader's primary job, is to simply find the Vulkan driver, and there could be more than one on the system. For example, if you have like an Intel CPU with an NVIDIA graphics card, there could be 2 Vulkan implementations on there. So it's the loader's responsibility to find the implementation that you want to run on, and simply allow the application to call into the Vulkan driver. Now, if you're familiar with Wiggle and GLX programming, and EGL programming for that matter, they're all different in the way they do this. And the goal of the loader is to kind of unify that. So in Windows, it's particularly bad for OpenGL, because you use Wiggle to load the original OpenGL driver, which supports version 1.1 of the API. And then you have to go through like extension wranglers and function lookups and all this kind of stuff, and to load all the functions that you need to use. But the Vulkan Loader eliminates all of that. It's one consistent component that does loading. And it has some really other cool features. You can actually inject layers into your application dynamically. So to add certain features. For example, if you run your application with the trace and capture layer added in, you can basically dump all the Vulkan calls to like a file and then play them back later. There's a validation layer which aids application development. So the application, it wants to use Vulkan to its full speed, which means the Vulkan implementations don't have a lot of error checking themselves by design. And so during development, you use a validation layer to check your application, make sure that you're not passing in any invalid arguments, and make sure that the application is obeying all hazards, and also that it's written to be platform independent. And then when your application is developed, you simply run Vulkan without the validation layer. And the other really cool layer is the debug layer. And this is something that LunaG kind of showed a little bit at GDC earlier this year. So with the debug layer injected, you can also, there's this tool called Glaive Debugger, which LunaG is developing right now. So you can actually have like full GUI-based debugging on your Vulkan application. And these are all tools and layers which are going to be provided by Khronos, and a lot of these are going to be open sourced for the public to see how they work and also to add to and contribute to. If you are curious about the Glaive debugger, there's a link here to LunaG's website, and they have a good video in there so you can see it running in action. So the application starts. It is use a Vulkan Loader to load the implementation. So for example, the NVIDIA Vulkan driver. The next thing it needs to do is figure out how to display content from Vulkan. So there's this set of extensions which Khronos is developing called the Windows System Integration, or WSI for short. And it's going to be a single consistent set of APIs that will be supported on Windows, Linux, and other platforms as well. And the idea is to provide the application just a consistent, easy way to run on any platform without having to figure out the details of doing display for that particular system. So for example, on Windows, the application might want to display their content in a window. They would create a window for their application in the normal way using Win32 APIs like create window. And then they'll use this WSI extension to tie the presentation of presentable images onto that window. And the same code that they use to set up for presenting on a Windows window, they can use for other system platforms as well. All right, so we've got the loader going, we've got our display going. Now the next step is we're going to set up all the resources we're going to use for drawing this triangle. In this particular case, drawing a triangle, all you need is some vertices and maybe even an index buffer. But this particular one doesn't have any textures or anything. But just imagine that there's a whole bunch of resources that you need to set up. So we're going to talk a little bit about that. So one of the things Vulkan has is a low-level memory API. And a lot of the ISVs have been asking for this. It's kind of like console-like access on any platform to memory. So the application basically allocates physical pages. And then when they have objects, like image objects or buffer objects, they have virtual addresses, but they have no memory backing. So before you use them, basically you can take your object and then bind it to a particular segment of your physical allocation. And it's the application's responsibility to do sub-allocation, which means you create a large physical allocation, and then you can put multiple objects in the physical allocation. And the reason you want to do your own sub-allocation is because doing the actual physical memory allocation can be expensive. And it is expensive. And if you do a lot of allocations on older APIs that aren't explicit, it's unpredictable. Sometimes when you make the allocation, it's really quick, and sometimes when you make the allocation, it's really slow, because behind the scenes, the driver's doing sub-allocations and all kinds of stuff in the background in order to try and make it look fast. When in reality, it's just become unpredictable. So this is one of the things that ISVs demanded, is that they have full control over memory. So when they allocate memory, it really does get allocated right there and then. And they can place their objects anywhere in the memory they choose. In fact, you can even take two objects that are compatible and place them over the same piece of physical memory. And you can use this for things like staging. Like you might want to populate that physical memory in one form and then use it in another form, for example. Another important thing about the Vulkan API is it has full support for sparse memory. And it actually supports a whole range of sparse memory feature levels, all the way from basically ARB sparse texture feature level, which is, you have to query the implementation to find out your tile size, all the way up to EXT sparse texture 2 level, which means that it has standard tiling sizes and features such as the shader knows whether a level of a texture, for example, is populated. And then within the shader, you can make choices about what level of MIP level you use. So the whole, what we know today about sparse memory, from the basic support all the way up to advanced support, all of that is exposed through the Vulkan API for applications to use. So Vulkan is an explicit API. It's a lower level API than GL, which means there's a lot of things that Vulkan application needs to do that used to be taken care of it by GL. For example, Vulkan, I mentioned before that you create physical allocations. There's actually different kinds of physical allocations you can make. Some are from the high bandwidth device-only memory, and some are from like CPU visible memory, which might not be as high bandwidth, but it's accessible by the CPU. Because the application cannot access directly the high performance memory, it's up to the application to create two buffers and stage the populating of that memory through the two buffers. And I'll go into a little bit how that works. And the other cool thing about Vulkan is that the transfer of memory from one place to another is all done through asynchronous commands and the asynchronous copy queue. Or you can use the 3D queue to do these copies. But the key is that it's asynchronous. So if you have like an application that needs to stream resources as the user moves around a scene and looks at different things, you can have a thread running in the background that's all its job is to stream in resources and make them available for the primary render thread. And that's something the application has explicit control over, which they didn't have before. So this is just a little example of how you would use a staging buffer to populate your device-only memory. So the application has its data, and it wants to copy into the high-performance memory. It goes through a CPU-visible staging buffer. The CPU-visible buffer you can get a pointer to, so you can just mem-copy your data in. And when you're finished mem-copying the data, then you record a copy buffer to image command, and then you can submit that command on one of the queues. It can either be your 3D queue or your copy queue. And now it's asynchronous. That transfer will end at some point in the future, but the application doesn't know exactly when, unless they use a fence. And the fence tells the application, OK, this copy is done. Now you can reuse that staging buffer something else. Or even if for more advanced uses, you can use semaphores, which you can use to synchronize between command buffers in flight automatically. So we have resources. Somehow we need to tie those resources into the shader, so the shader uses the resources. Here's an example of what a shader might have. So here, this shader has two resources. It has an image and a sampler. And it gives binding numbers for those resources. And so somehow we need to tie a particular piece of memory with that resource that the shader is going to use. So we do that through descriptor sets. Descriptor sets is something that can typically change quite frequently during your rendering as you're using different materials and different textures and stuff like that as you're drawing the entire scene. So this is something that needs to be fast. So we do that by allocating descriptor sets from descriptor pools, which means that lots of different threads can allocate descriptor sets and update descriptor sets simultaneously with each other. In a descriptor set, once you've set all the different binding points, what resources you want to use, then right before you draw, you bind that descriptor set, and then the draw will pick up all the new resources. And here's just a little more explanation of how that might work. One of the really cool things about Vulkan descriptor sets is that it supports multiple descriptor sets. So in the shader, for example, this shader has 3 different kinds of resources that it needs to use. It has resources that only need to update per scene, resources that update per model, and resources that update per draw. Of course, the ones that need to update per draw, they're changing very, very frequently, and the model ones changing less so. So you can partition your resource usage into sets. And then this is a little bit of pseudocode to show how in your inner draw loop, you're only modifying all the draw resources, the per draw resources. And then when you're done with all your draw pools and you move on to the next model, you update both the model and the draw resource. And then, so the high frequency stuff, when you do high frequency descriptor changes, it doesn't affect the low-frequency stuff. And this is an improvement in optimization. Updating descriptor sets and binding new descriptor sets is one of the most performance-critical parts of Vulkan. So getting it as fast as possible is very important.
Sorry, can I ask a question quickly?
Yeah.
Is this also like including texture state and other stuff?
Yes, thank you. Yeah. Yes, thanks. Yeah, inside descriptor sets is all the bindings that you need for a shader. So a shader would use images, samplers, buffers for UBOs and SSBO. So moving on through a Hello Triangle. So the next thing we need to do, we've launched our driver. We set up our resources. Now we need to set up the 3D pipe. The 3D pipe is described by a pipeline state object, which I'll talk about in a little bit. And the pipeline state object has shaders, and it has 3D state. For Vulkan, the only way to get a shader into Vulkan is by passing in SPIR-V. SPIR-V is a Khronos-defined standard. It is an intermediate shader representation. And it's a portable representation that can be used across platforms. And it's something that you can compile from a high-level language down to SPIR-V offline. One of the things that Khronos is going to provide is a front-end tool, which you can use or you cannot use. You can use your own if you want. But the advantage of having SPIR-V as the only way to get shaders into Vulkan is that the implementations don't need to implement a front end. And one of the biggest complaints about OpenGL is the inconsistency of GLSL compiling between implementations. And so SPIR-V is designed such that you can have a consistent front end across all platforms, generating the SPIR-V. So some of that inconsistency is filtered out right at the front end. There's consistent semantics. And then doing a little bit of compile offline can save some compile steps. But the implementation still needs to convert from the SPIR-V down to their machine code. So it doesn't save all compilation steps. So the SPIR-V spec, provisional spec, has already been out. I think it was released at GDC. And Khronos is going to support a open source GLSL to SPIR-V compiler called GLSL Slang. And ISVs can incorporate this tool or any other tool they like, whatever their high-level language is, into their content pipeline. And as long as what they output at the end is SPIR-V, it'll work well with Vulkan. And since the spec is already published, this preparation work on your content pipeline can start today. Another unique and cool thing about Vulkan is the Vulkan shader object. So when SPIR-V is passed into the driver has the opportunity to right then compile the SPIR-V down into its machine code, if possible. There are some state-dependent compiles which will stop it going all the way down to machine code in some cases. But it can compile a lot of the code right down. And then this same shader object can be reused for lots of different pipeline state objects, which I'll talk about in just a second. And the other cool thing is that the shader object can be an Uber shader with lots and lots of different entry points. And when you use that shader object in your pipeline state object, you can just say, OK, I have this giant compiled shader that's compiled down to machine code, which I've done once. And I simply want to execute function 1. Or I want to execute function 2 when the draw command is executed on the GPU. And this is a great way of reusing work over and over again without having to do compiles or compile common code over and over again. So now, finally, the pipeline state object. So this represents all the static state for your entire 3D pipeline. So this is the shader. This describes the vertex shader inputs, how you want to rasterize. So, example, if you're drawing lines or solids, or your color blend functions, and depth stencil state and stuff like that. Now, the pipeline state object was carefully designed such that all the state in it is the kind of state that might invoke a shader recompile on an implementation. So by unifying all the different states that could invoke a shader recompile across all the different implementations, we have a single pipeline state object where you can do all the work up front and know that once you've baked in your pipeline state object, you won't get another shader recompile, which is one of the limitations of other APIs, in that sometimes just when you do your draw call, suddenly the implementation goes off and does a shader recompile, and you didn't ask for it. But now, with a pipeline state object, all the shader compiles is done in the pipeline state object, no more. So that when you switch between different pipeline state objects, when you're doing your drawing, you know that there's no shader compiles happening in the background. And the other cool thing about pipeline state objects is that they can be cached, which is really cool. Which means when an application builds their pipeline state objects, which can be a lot of work, because don't forget, we were compiling our SPIR-V down to machine code and figuring out all those different states and how to program all the hardware and baking that in to the pipeline state object. There can be a lot of work going on. And this is not the kind of work that you want to do. You definitely don't want to do it while you're actually traversing your scene. This is stuff you want to do up front. So not only can you defer the building of pipeline state objects, I don't mean defer, I mean do it up front. But you can also save the work you've done on previous invocations of the application for new launches of the application. And in fact, the other thing that we've added to the API is the API has a unique UUID, which represents the device. So an application developer, for example, could bake a whole ton of pipeline state objects and associate them with a particular UUID. And when they distribute their applications, they can have a whole range of UUIDs, all with baked pipeline state objects that can be used again. So this improves application startup, and it can remove glitches between scenes of your game. And it's a really cool thing. In fact, you can even, an application might save the pipeline cache out to the cloud, such that the first user to ever run a game might see a couple of hitches on startup, but all other users from then on, it'll be plain sailing. Now, the pipeline layout is something that describes the mapping between shader resources and the actual resources themselves. And one of the unique properties of a pipeline layout is that it allows you to create compatible pipeline state objects, so that when you switch between pipeline state objects as you're rendering different materials or different parts of your scene, you don't have to reprogram your entire descriptor set. They can remain compatible. And like I said before, updating and changing descriptor sets is going to be one of the most performance critical parts of rendering in Vulkan. So a pipeline layout will allow pipeline state objects to stay compatible with the descriptor sets and improve performance. And finally, for setting up the 3D pipe, we have dynamic state as well. All the state that's in a pipeline state object might affect shader compilation on some platforms. But everything else left out that doesn't affect shader compilation is put into dynamic states. And these are things that can be changed very, very quickly between draws. And some of the things that you can change, as I've enumerated here. But any other state has the potential to cause shader compiles, so that's why they're in the pipeline state. All right, so we've set up the 3D pipe. We've got our pipeline state object and our dynamic state. Now, the next thing we're going to do is record the commands for rendering this triangle. Now, a render pass represents a unit of work. I mentioned up front that Vulkan is something that's designed for mobile platforms and designed in such a way that mobile platforms run in the most optimal way. And one of the ways we do this is through a render pass. Now, what a render pass does is it tells you how to populate your frame buffer cache before you do any rendering. So, for example, do you need to transfer data from the real frame buffer into your frame buffer cache? Can you just clear it to a value? or just ignore it. And then at the end of your render pass, this object tells you whether you want to save the results back to the frame buffer, do a multi-sample resolve, or just discard the results. For example, if it has side effects, you can just discard the results. And one of the coolest things about Vulkan is that you can chain multiple render passes together to create like a single multi-pass. And there's enough information when you chain these render passes together that describes the dependencies between each render pass. And if your algorithm, for example, has multiple steps in order to create its scene, like for example, it creates the G buffer, it does light accumulation, it does final shading, and then it does post-processing, 4 different steps, you can execute all 4 different steps all on one tile without ever going to and from the frame buffer, which is awesome. This is something that mobile hasn't had until this point. And the important thing about this is that one of the most power-hungry things to do on a mobile device is to do memory transfers. And that's why the big difference between mobile and desktop is its ability to do memory transfers and how fast it can do them. Because it's just too power-hungry to support fast memory transfers. And one of the biggest consumer of memory transfers is going to and from the frame buffer. So by allowing a tiler cache, for example, to execute all 4 steps of this algorithm, all within one tile, without ever going to and from the frame buffer, is huge. It's a huge win for mobile. And it's the kind of thing that will raise the quality of graphics on mobile for everybody. And if the quality of graphics is raised on mobile, it's good for all of us, the industry, because mobile devices represent, like, for example, 1 billion users of OpenGL ES. Imagine if they had this kind of way of saving bandwidth and improving their graphics. So this is a really big part of Vulkan. So in order to generate work for the GPU, you record command buffers. A command buffer is basically an opaque container of GPU commands. And once you've finished recording a command buffer, then you submit it to the GPU for execution. You submit it to a queue. There can be more than one queue on your system to run different commands in parallel. So commands are added when you're recording a command buffer. A memory for the command buffer is allocated from a command pool. Multiple command buffers can be allocated from the same pool, and I'll explain why this is important in a sec. So here's an example of recording a command buffer. The first thing we do when we record a buffer is start a render pass. We bind all our resources, so there's lots of binding calls going on. We modify dynamic state, and then we draw. And all the parts between start render pass and end render pass, you call those as much as you like in order to render the scene that you want. Obviously, don't do redundant state changes if you can avoid it. But it is designed, Vulkan is designed such that recording a command buffer, doing all these different things, which could be, it could be tens of thousands, hundreds of thousands of draw calls, depending on what you're doing, is designed so that recording this is going to be fast. Command buffer recording performance is critical to Vulkan. So one of the things that command pools offers is a way for command buffers to allocate their memory without lock contention. So you can have multiple threads all building command buffers simultaneously. So you're utilizing your CPU to its full potential. And when these different CPU cores are building their command buffers, they don't fight on locks. And if they don't fight on locks, it means they can run in parallel, and you get really good multi-CPU scalability. So this just talks a little bit about maximizing multi-threading. So I just mentioned the command pools are designed to allow command buffer building across multiple threads. We also have a bunch of other features in Vulkan to help your applications run in parallel as much as possible. For example, our descriptor pools allow multi-CPU descriptor set allocations. Resource creation do take locks. But as I mentioned earlier, this is something, if you're streaming resources, this is something you can do in a separate thread. Those locks don't contend with, for example, command buffer building. They do contend with other resource allocations. So if you have two threads both allocating resources at the same time, you might hit a lock. But if you do all that kind of stuff on one thread, off the performance critical path, then in general, your application is not going to have problems with lock contention, and it's going to run as multi-threaded friendly as possible. Just briefly, Vulkan supports compute. It's a first-class citizen of the API. You can issue compute work between your 3D work, and it shares resources with 3D. One of the things about Vulkan is that it's the application's responsibility to deal with resource hazards. I want to do some demos, and I'm actually running longer than I thought, so I'm going to just zoom through some of this. One of the things, so it's the application's responsibility to deal with hazards. OpenGL used to do this, and OpenGL used to have to track state and figure out the dependencies between different uses of your buffers. Now it's the application's responsibility. For example, if the application is updating an image buffer with image stores, and then they later on a separate draw call want to consume those updates from the image by sampling the image, they have to be explicit. They have to tell the implementation that, okay, I'm done writing to this image buffer. Now I want to read from it. And then the implementation might put in some, for example, it might invalidate or flush the image store caches and then invalidate the image sampling caches. So we've built the commands, we've got all our resources. Now we have to submit the commands to the implementation. Vulkan exposes multiple queues, 3D queues, compute queues, and DMA or copy queues. And it even supports a universal queue where a queue can do all three of those things. Queue submission should be cheap. All the work on the CPU by the application is done building command buffers and changing descriptor sets. That's the idea. The actual submission of that work on the queue should be cheap. And then queue execution is asynchronous. And the app can use fences or semaphores to synchronize work between command buffers on separate queues. So we've finished rendering our triangle to a presentable image. Now we need to present that image on the display. So this goes through the WSI extension. The WSI extension is designed to asynchronously allow you to present your data without blocking the rend thread. So basically, you give it an image to present. When it has an image available, it will give one back to you, and then that's the next image that you render to. So your display pipeline can be nice and asynchronous and flow without blocking. Now I'm going to show a brief demo. This is work in progress. Kishanti are developing this new GFX Bench 5.0. And the idea that they have is that they want to support all the new next generation APIs. So this app supports Vulkan, DX12, and Metal. This is still an alpha implementation, but it's going to show a couple of important things. So let me just start that up. So I'm running it on a MacBook, but don't be confused, it's actually running Windows 10. All right, let's see. So this is the demo. Now this is work in progress. They actually have a newer model, a newer version of this demo, which has all kinds of particles and dynamic scenery and stuff. We don't have that running yet. In fact, getting this running on Windows 10 was something I just did in the last 2 days because I thought it'd be fun to show Vulkan running on Windows 10 first. You saw it here first. And actually, a later version of this demo, not only does it look a lot better, the performance has been improved substantially. My laptop is not the most powerful laptop in the world, but it just shows you that Vulkan is working and people are working on it. It's a real deal. There you go. You can see it's Windows 10. That would be a real cool thing if I could get it working on OS X. All right, let's talk about Vulkan on NVIDIA GPUs. Vulkan is really important to NVIDIA. Why is it important? Basically, it's open. And why that's important is that when we release new GPUs, we can expose new features on those GPUs through this API without getting permission from the platform vendor or some other person who controls the API. The API is extensible. And this API can support all our chips. It can support from Tegra, which I'll show in a little bit, and it can support all the way up to the highest power workstations that we ship, which I'll also show. But what about OpenGL? Well, OpenGL is also vitally important to NVIDIA, and it always will be. Together, OpenGL and OpenGLES still remain the largest 3D API in the market. And we support all these different kinds of applications, and we will continue to do so. In fact, this year, since Vulkan efforts started, like in June last year, we've still been putting a lot of effort into improving our OpenGL. For example, when our Maxwell chip was released in September, we released 15 new extensions. And we have other important work going on in OpenGL, for example, NV command list. And maybe there's more coming in for OpenGL. So find out at the BOF if you guys are going to the Khronos BOF, which I'll mention in a second. So OpenGL and Vulkan, no one is better than the other. They solve 3D in different ways. It's arguable that OpenGL is going to be easier to use. It's easier to teach, easier to prototype in. OpenGL drivers do a lot of things for you automatically. You don't have to worry about hazards and dependencies and stuff like that. OpenGL can be used efficiently if you're careful. It has fantastic single-threaded performance that can even approach Vulkan if you use NV command list, for example. But Vulkan's ace, the thing that really separates Vulkan, is the fact that it scales well across multiple CPUs. And we don't have that yet in OpenGL, yet. So Vulkan on NVIDIA GPUs, like I mentioned, it supports all our products from Tegra all the way through to our fastest. The idea is you can write your application once and run it across a whole range of different products. So we have basically 3 different architectures which will support Vulkan: our Fermi, Kepler, and Maxwell architecture. And on the right is the products which are using those different GPU architectures. Our implementation of Vulkan across Fermi, Kepler, and Maxwell support all OpenGL ES 3.1 level features, all OpenGL 4.5 level features, and have varying support for sparse memory, depending on the platform. And then for the ETC2 and ASTC, these are mobile-orientated texture compression formats right now, and so only our mobile parts will support those. So, and we will support Vulkan OS on multiple of different operating systems: Windows XP through 10, Linux, SteamOS, and Android where we can on Shield tablet and Shield Android TV. So I'm going to show a little walkthrough and demonstrate some of the things that make Vulkan great on our implementation. This is CAD scene demo application. This is something you can get the source for. If you just Google it, you'll find a GitHub location where you can download the source for this for GL, the GL version. When Vulkan ships, we will try and ship a Vulkan version of this for people to play around with. But one of the unique things about this application is that it mixes both OpenGL and Vulkan together. So our implementation of the Vulkan driver is hosted by our OpenGL driver. And the great thing about this is that anywhere that we can ship our OpenGL driver, we can ship our Vulkan driver as well. And there's a lot of leverage we can get between OpenGL and Vulkan. However, if a Vulkan-only application is using just Vulkan, the OpenGL part of the driver is dormant, and they get full performance. And if they want to use OpenGL and Vulkan, they can. And in fact, they can even share resources between them. However, it's important to note that if they're using OpenGL, it's not affected by Vulkan in terms of, it doesn't slow it down in any way, and vice versa. So the Vulkan parts, even if they're using OpenGL as well as Vulkan, the Vulkan parts run at full speed. So benefits of mixed driver. It makes it easier to transition to Vulkan. You can incrementally change your OpenGL app, for example, if you have a big existing app. You can incrementally add Vulkan to it. And CAD Scene is an example of that. So here's some things you can do to get your existing legacy OpenGL code. If you wanted to move to Vulkan, to be more Vulkan friendly, you can take incremental steps. For example, you can convert your application to use ASDO techniques, as presented there. This is something presented a couple of years ago. You can start using NV command list, which is kind of Vulkan-like, in that you create command lists and you execute them on the GPU. And then finally, the most important parts of your performance critical parts of the API, you can actually just port over to Vulkan. So I'm going to show you how we meet some of the goals of Vulkan. Reduce CPU overhead, scale well with multiple threads, predictable no hitching, and multi-GPU support. All right, so all right. Now, this application is running in GL mode right now. You can see that the renderer right here is GL uncached mode, which is just using the GL core API. And you can see at the top here, hopefully you can see that well. You can see the time spent on the GPU and the time spent on the CPU. So the lower that number, the better it is. That's the amount of time that we're spending on each of those things. So this is showing it rendering in GL. And so there's GL running there, and all this UI is all GL as well. So let's move over to Vulkan mode. And then you can see how the performance, the amount of time you spend on the CPU has gone down substantially. And here we're running this code. This is all Vulkan right now, and this part of the code is still OpenGL. And you can see how Vulkan has substantially reduced the amount of CPU time to render this object. Now let's show some other stuff. So let's go back to GL mode. You can see the CPU time go up again. Now let's do tons and tons of shader changes. So now between each draw call, we're basically changing shaders. We draw a solid, and then we change shader to draw the lines, and then go back to solid, line, solid, line, solid, line. This happens 5,000 times a frame. So you can see the CPU usage in order to do that has gone up a lot, for GL. Now if we switch to Vulkan mode. Oh, okay, yeah. So the CPU time right now is 10,000. And then when we go down to Vulkan mode, we've dropped the CPU time down to 6,000. So you can see a saving there. Right, so this is one model. Now I'm going to show another model. So this one has about 100,000 draw calls per frame. And then you can see that our CPU usage for GL is 5,500. Now if we switch to GL, we can see our CPU usage drop down to 1,100-ish. Now I'm going to show you something really cool. All right, so I'm going to increase the number of threads that are used to build this model. So we're starting at about 1,100 CPU usage. Now I'm going to add 2 threads, and check out that scaling. That's pretty good. We've gone down to 650 by basically just doubling the number of threads rendering this model. That's something that you can't do on the older APIs, is that amazing thread scaling. All right, now I'm going to do one last one. And fingers crossed this one actually works, because this one is huge. So this model that's loading right now, I'll show it as soon as it's loaded, uses 220,000 draw calls per frame. And the thing, between each draw call, there's a UBO change and a VBO change. So this is a ginormous model. In fact, you can see how big this model is. If I just show you, oh, you can't really see it there. But anyway, this is the model running. It's taking 2.7 gigabytes of memory in order to render that model. So it's ginormous. So here we are in GL mode. Let's switch to Vulkan mode. And so we're going from 34,000 CPU usage. I'm specifically not giving units for this because it's the relative change is the most important thing. So we went from 34,000 down to 6,300 CPU users to generate this ginormous 220,000 draw calls per frame model. Pretty cool, huh? All right. And now I'm going to show you Vulkan running on our Shield. So I have this same application running on Shield as well. And we ported it to Shield by using our GameWorks cross-platform SDK. So this is something that you can see samples for on the web right now for GL and stuff. But it's an environment where you can develop apps for Windows, Linux, and Android, all within the same development environment. So for example, here's Visual Studio. There's a GameWorks project loaded up here. And you can target Windows, or you can target Android, and you can build, deploy, and debug on Android right from Visual Studio. So that's how we developed this application to run on Shield. So now I will flip over to my Shield, which is this guy. It's our Shield portable. This has a Tegra X1 in it. All right, and then load our Vulkan prototype. So there we go. We have the model running 60 frames per second on our little Tegra X1 chip. Super smooth. This model has about 11,000 draw calls per frame. So let's tax it a little bit more. Takes a while to load. These are big, big files. This file is like 200 and something megabytes just for the image data. I mean, the geometry data. And there you go. Our Tegra X1 doing 110,000 draw calls per frame, running at about 23 frames per second. It's pretty good. Okay. So, how do you get a Vulkan driver? Well, the spec hasn't quite been released yet, so if you're not a Khronos member, you won't be able to get one yet. You can always become a Khronos member and then sign an NDA with us, and we'll happily give you a driver and a bunch of samples to play with. But after the Vulkan spec is released, hopefully later this year, you'll be able to download a Vulkan driver from NVIDIA.com. That is our goal. So if you're hungry for more information about Vulkan, there is more of it. There's a course on later today that's going to have a little bit on Vulkan in that course. And then the big course that's going to involve Vulkan and actually other next generation APIs is on Tuesday between 9 a.m. and 12:15 p.m. That's definitely worth attending to find out the state of the union for next generation APIs. And then on Wednesday at 5:30 p.m., there's going to be a State of the Union presentation by Khronos on OpenGL, OpenGLES, and Vulkan. And then after that, there's going to be a party. So thank you. Thanks for coming to this talk. But before you leave, don't forget to pick up your free Khronos t-shirt. They'll be outside. I'm wearing one right now. And you can pick up some and please wear them around the conference. All right, thank you so much.
Thank you, Piers.